All right. Welcome everybody to the GOCC. To remind you, we have our community statement, which says that we are all learning, everyone has something to contribute, and no one has all the answers. And today we are going to have Teresa Chambers talk to us about comparison testing of clustering with iterated linear optimization. All right. Go ahead.
All right. Hi, everybody. I've met some of you, but not most of you. So I'm Teresa. I'm a fourth-year student at Brown. And this is the work I've been doing with my advisor, Dr. Caroline Clavins. So there's an awful lot of terms in the title of that presentation that I'm going to need to go through sort of one at a time, but I want to start with sort of the main focus of my research, which is going to be the algorithm itself for iterated linear optimization. I'm going to tell you a little bit about what it is, where we're working on it, and why we're interested in it. And then I'm going to go through some of the current ongoing investigations that I've been doing with this algorithm and where it's headed in the future. So to start with, iterated linear optimization is an algorithm that operates on compact convex sets within Rn. We're going to define our algorithm T to be the following. For a particular point X, T will maximize the dot product of X over all elements Y in our desired compact convex set. So that's the base structure. And then what we're really interested in is applying this algorithm over and over and over again. We're iterating it. And what we're doing as we iterate is we're looking for a point where iterating the algorithm yields the same output as we had input. And that's what we call a fixed point. So as we do this, we construct a sequence of points xi, and we're looking for the point where xi thrown into our algorithm yields the same xi plus 1 as itself. So as a quick sort of example of how this might work, we can consider just a really straightforward compact convex set, that being a circle in R2. Can you guys see my mouse? Fantastic. So this circle is off center. All right. So a key point of this is that this point marked O here is the origin, but the circle's center is off over here. All right. So if we started with x0 down at the bottom of the circle here, what you would find is that the first time you apply t of x0, you'd go to this point x1. Apply it again, you go to x2, and again, and again, and again, and you're moving up to this point A. And actually, if you start anywhere inside or outside the circle, you'll end up at this point A. So we call it an attractive fixed point because it's pulling the algorithm towards it as you iterate. Now A has a counterpart R down at the other end, and R is what we call a repulsive fixed point. What I told you a second ago is kind of a lie. There is exactly one point in R2 where if you start at it, it won't go to A, and that's if you start exactly at R. R is a fixed point. If we plug R into the algorithm, we'll get R back out. But if you start anywhere other than R, you'll move away from R and towards A. So A is for an attractive fixed point, R is for a repulsive fixed point. Now, the thing about this is that circles are kind of simple, right? Let's take something a little more complicated. And so what I'm going to introduce here is a particular geometric structure known as the elliptope. Now, the elliptope is actually defined using the space of symmetric positive semi-definite matrices. The elliptope Ln is the subset of symmetric matrices such that they are both positive semi-definite and have entries of ones all along the diagonal. It's important to note here that n is not the dimension of the elliptope. It is the dimension of the matrices that define the elliptope. The dimension of the elliptope is actually n times n minus 1 over 2, because that is the number of degrees of freedom in this collection of matrices that we're using to define it. Unfortunately, what this means is that we can only really draw what the elliptope looks like for n equals 3, because that actually spits out R3 as well. And so what you can see when you have this is that the elliptope is sort of like a puffy tetrahedron. It gets exactly 4 sharp corner points. And those specifically are what I'm going to refer to as the vertices of the elliptope. They're symmetric matrices of rank 1, whose entries are all either plus or minus 1. But it's worth noting here that not all symmetric matrices with entries in plus or minus 1 would actually give you vertices of the elliptope. The rank 1 bit is really important in defining these. So if you look at this figure on the left, you'll notice that the vertices are marked in red. And then I've got a couple of other types of points marked in green and in blue. The points that are marked on this figure are the fixed points of our iterative algorithm on the elliptope. Now, the red ones are attracting. The green and blue ones are the midpoints of these sort of straight edges. That's a poorly defined term on the elliptope, but I'm going to use it for right now. They're the midpoints of these edges, and they attract along the faces. So if you start on one of these puffy sides here, you'll move towards the green, but they're repulsive along the edges themselves. If you're on one of the edges, it'll push it off to one of the vertices. And then the blue ones are just straight up repulsive. They'll push the algorithm away every time.
So a quick point of clarification: the elliptope is not a polytope because it
is not
curvy. Okay.
Yes. Yeah. So I can talk about vertices because it has these sharp corners that have like full rank normal cones, similar to how you would for a polytope. However, unlike a polytope, the other points on the surface are all going to just have like a single direction, and that's not going to be the same in different parts of what one might consider a face.
Sure.
The edges are one-dimensional and affine, which is why I'm kind of calling them edges, but because they're only really defined by the presence of the vertices.
So they are the convex space between the vertices, and they don't bend outwards, but that's about all you can say about them.
Pretty much. I think this figure on the right sort of conveys the issue pretty well, because if you look at this like green surface, the edge between those top two vertices is not distinct in any way, shape, or form, aside from the fact that it's a straight line connecting the vertices. Other questions? All right, now before I tell you why we care about the elliptope, I'm going to make things a little more complicated. So we don't just care about the elliptope for our purposes, which I shall elucidate in a moment. We're actually really interested in a variant structure on the elliptope, which we're going to call the K-way elliptope. And the K-way elliptope is basically obtained by slicing off chunks of the elliptope using affine surfaces. So we add an additional constraint to the elliptope where, we're not just looking at the space of positive, semi-definite, symmetric matrices with ones along the diagonal. We're also adding this constraint that every entry has to be greater than or equal to this value minus 1 over k minus 1. So looking back at our n equals 3 case, if you think about it for a second, you'll notice that if I put in k equals 2, that wouldn't actually accomplish anything, because that would put the constraint of xij is greater than or equal to -1, which ends up just being the case for the elliptope in general regardless. But if I use k equals 3, now I've got that all xij have to be greater than or equal to -1/2. And so since we have for n equals 3, an object in 3 dimensions, 3 different degrees of freedom for the matrix, what that introduces is 3 planes that slice off the elliptope, 1 for each element. So at this stage, I've removed the non-vertex fixed points from the diagram of our main elliptope, because what I'm really interested in is the impact of this slicing on the number of purely attractive fixed points. In the original elliptope, we have 4 attractive fixed points, 1 for each vertex. By adding these slices, what we actually end up with is 5. We preserve one of the original corners, and then we've got this polytopal portion of the surface that creates the remaining fixed points. So why do we care? How is this useful? Well, it turns out that there is actually a bijection between the k-way elliptope for n-dimensional matrices and the ways to partition a collection of n items into up to k groups. So if we look back at the original elliptope, remember I said that was pretty much identical to the case of k equals 2. So one vertex would represent the partition where you put all 3 items in a single group. And then the other 3 vertices represent the ways that you can put 3 points into 2 different groups. When I raise k to 3, we get this extra vertex down here that wasn't there before. And now that one is going to represent the partition of the 3 vertices into 3 different groups. And this scales up as you increase both n and k. That relationship remains. And that is the relationship that we're really interested in. And that's why we're focused on these particular objects, because what we really want to do is figure out a way to use our rounding algorithm that can get us to these vertices to solve clustering problems. Okay, so there's another term that I'm probably going to need to talk about a bit. What is clustering? What does this mean? In general, what clustering is about is finding a partition of endpoints that is going to be in some sense optimal. Now, what optimal means is going to depend a little bit on the data and the context, but generally speaking, the idea is to maximize the similarity of points in the same group, or the difference of points that are set apart into different groups. There's a couple of little snags in that particular ideation of the problem. Number one, if you think about real world data, you're not always going to know how many groups you're trying to partition your data into. That's sort of part of the question that's usually trying to be solved. So current algorithms, what a lot of them will do is they'll solve the clustering, they'll try to solve the clustering problem for a bunch of different values of K, a bunch of different numbers of groups to sort things into, and try to see which one gives the best results. One of the other problems is what I'm trying to represent with these two figures here, which is that the notion of maximizing similarity of points in the same group can be done in very different ways depending on how you're sort of quantifying similarity. So this is an example. This data set has been clustered using two different very commonly used computer algorithms. This one on the left is the result of k-means, and this one on the right is the result of spectral clustering. The numbers in the bottom left corner are how long it took each algorithm to put out its results. And so what you have here is that k-means was a lot faster, but k-means sort of looked for like centralized, nice round little balls of points that it could put together. Spectral clustering took significantly longer, but produced results that we can look at and say, yeah, that matches the shape of the data as we can see it. The vast majority of data that's produced and that needs to be clustered is not two-dimensional, so we can't very easily check it with a visualization like this. So the question of how to find algorithms that are going to regularly and reliably cope with very unusual data structures is a pretty important one. But that does bring us to sort of another problem. A clustering problem is inherently combinatorial. We're looking for some sort of optimal partition. Now, unfortunately, this doesn't really play ball well with the actual process of optimization. Optimization generally works best with nice, well-bounded but continuous domains. Something like, say, an elliptope. And that brings us to the other key thing I want to define before I get into how this is all going to come together. So some of you may have heard the term spectrahedron before. Mark, you mentioned polytopes earlier. Spectrahedra is a generalization of polytopes outward to be a little more relaxed. Generally speaking, a spectrahedron is an intersection of the cone of positive semi-definite matrices with some affine space. So the elliptope would be an example of a spectrahedron. Any polytope will be an example of a spectrahedron. An awful lot of shapes that you can think of off the top of your head are probably going to be spectrahedra. And the reason I need you to know that term is because we're going to be using a process called semi-definite programming. In general, this looks like an optimization problem with some cost matrix C, variable matrix X, and constraint matrices A, where our variable matrix has to be positive semi-definite. The thing about semi-definite programming problems, without digging too deep into the specifics of how that would actually work, is that any semi-definite programming problem will have a spectrahedron as its solution space. And in fact, any spectrahedron is the solution space for some semi-definite programming problem. So what that means is that if we're interested in the elliptope with its vertices that represent partitions, or the K-way elliptope with its vertices representing even more partitions, those objects are the solution spaces for semi-definite programming problems. And that means we can do something pretty useful, which is if we have some set of data points, we can put them together. We can gather information on something like, say, the Euclidean distances as a first effort between the different data points. We can throw those in a matrix. That matrix will be positive semi-definite, and so we can use it to construct a semi-definite programming problem, and solving that problem will give us a matrix on our K-way elliptope. Now, what I'm not going to do right now is I'm not going to tell you about what specific semi-definite programming problem is actually going to do this for us, because what I really want to focus on now is that what semi-definite programming is not going to do is put us at a vertex. The vertices are what we're interested in. The vertices are the partitions. So we need to get from the matrix that we land in to some vertex that represents a partition. That will be the solution to our problem of grouping our data points. And that is where we come all the way back around, full circle, to the iterated linear optimization. We take the solution from the semi-definite programming problem, we run iterated linear optimization over the compact convex space of the K-way elliptope. That takes us to a partition. That's a solution to the clustering problem. Great, that's a method. So let's take a little bit of a look at how this actually works. In order to test how this algorithm would actually function, I tried a couple of things where I would randomly generate two-dimensional data so that I could actually visualize and see where the natural clusters were forming in the data sets. And then I used our semi-definite iterated linear optimization method to cluster the results. And I also used that very popular clustering algorithm I mentioned earlier, the k-means algorithm, to cluster the results. So one example of that would be in this particular figure, I have sampled data from a bunch of nice distributions that are evenly spaced around the unit circle. They are Gaussian distributions, which basically means that the data is nicely centered and like the likelihood of getting an outlier from, say, this black grouping all the way over here is very low. And so one thing that I made sure to do in order to test this was I took note of my true number of clusters. In this case, it's 8. And then I fed both algorithms a wide variety of numbers of clusters to look for, right? Remember, I mentioned most algorithms, you try a bunch of different possible k values and then sort of see which one gives you the best results. But the benefit of using this iterated linear optimization and this K-way elliptope semi-definite programming structure is that, in fact, when you provide a k value that is higher than your true number of clusters, the correct partition, so to speak, will still be somewhere in your resulting solution space. If you have the 10-way elliptope on 80 data points, then that object has vertices that represent partitions of those 80 points into 8 groups as well. And in this particular example, that is in fact what happened. For k-means, when I told it to look for k clusters, or 10 clusters, excuse me, it did in fact spit out 10 clusters, which is very reasonable. You can see that it went ahead and found all 8 of the true clusters pretty well. It's not mixing and matching points from different clusters, which is great. That's, it's always nice to see. But then it went ahead and it broke up this cluster here and this one over here to meet its quota of 10. By contrast, the iterated linear optimization was able to find the optimal partition of only 8 blocks. Now that's all well and good. But another way, this is useful for data sets where I can actually see the correct groups and know what's going on. But it's also useful to have a broader scoring metric to get a sense of what's going on. So I looked at 2 different metrics for measuring clustering performance. One is called the adjusted RAND score. For adjusted RAND, higher is better with a maximum of 1. And that's because the RAND score is used in cases where you do know the ground truth of the clustering. So this one's really good for when you're doing, careful experimentation like this. And what you can see here is that I've got the K values I tested along the x-axis here, and K-means had some poor results for low K values. For K equals 8, K-means did find the correct clusters. And then after that, the results dropped off. Now, if you were just looking at K-means, you'd look at that and you'd say, okay, well, 8 clusters got us the highest score by far, so the true number of clusters seems like it's probably 8. For iterated linear optimization, the scores look a little bit different in 2 main ways. Number 1, it got the perfect score on K equals 10 as well, but the reason for that is because it dropped down to 8 clusters. So if you combine that information with the inputs, you have that 8 clusters is even more likely to be the true number of clusters, because when searching for more than 8 clusters, the algorithm determined that the optimal solution was to drop back down. The other really important factor of this is that for very high and very low numbers of clusters, what we have is a much sharper drop off than for K-means. So for K equals 12, they got about equivalent results. But for K equals, I believe this was 16 and 20, the strength of the clustering for iterated linear optimization dropped off much more considerably. Now that sounds like a bad thing, but it's actually a good thing, because that's stronger evidence in favor of the idea that 16 clusters or 20 clusters is just too many clusters and doesn't make sense with this data set. Similarly, on the other side of things, we've got low numbers of clusters, 3, 4, 5, and 6. And the sharper this drop off here, the stronger the evidence is that those low numbers similarly do not match with the information on the data. So that came out pretty well. But the one big downside to this is, of course, that the RAND score requires knowledge of a ground truth. In a real world setting, you're not going to have knowledge of a ground truth. That's the whole point of the problem. So I also wanted to test how this would look in comparison to K-means with a clustering score that did not rely on ground truth. And that's where the Davies-Bouldin score comes in. For this one, lower is better. We want to get down as close to 0 as possible. With Davies-Bouldin, you'll generally find that it takes extremely nice data to actually get a 0. There's really no such thing as a perfect score by this metric. But once again, what we have is that the semi-definite programming got the same score for 2 of its clusterings, k = 8 and k = 10, because it dropped down from using 10 clusters to using 8 in that iteration. And even more compelling is if you look at the scales on the y-axis here, you'll see that as the number of clusters was increased after 10, the Davies-Bouldin score of the ILO results got dramatically worse. Now, it is generally a thing in clustering analysis that for scores like this in messier data, what you might sort of see is that a score will gradually improve up until some point. And then it'll either have sort of a sharp elbow shape like this, or more realistically, it'll probably just continue improving, but not as rapidly as you go up. And the messier the data, the less of a shift you'll see there. So being able to get this really dramatic change means that there's a good chance that iterated linear optimization could handle much less nice looking data and still produce results that lead you to the correct number of clusters. So let's test that theory. Taking this algorithm out of my nice, neatly crafted, well-generated, cleanly separated data set, we're going to look instead at data taken from the MNIST database of handwritten digits. This database, every digit consists of a 28 by 28 pixel assortment of zeros and ones, basically, where someone's handwritten version of 0, 1, 2, 3, and 4, and so on, has been converted into an image. Now, what you'll notice looking at these digits is that there is a wide range of variation within a particular set of digits. The zeros are kind of okay. The ones have a pretty broad assortment of slant choices to them. And then the fours, you can forget it. So the interesting thing about this data set is that if you just take the raw images and you choose a bad distance metric, basically, no machine learning, no pre-processing, just what is the like basic Euclidean distance between these two like sets of vectors, they're not going to look very similar within a particular group. Thankfully, that's the point here. And also, interestingly, provides a useful commentary on the need for functional computer vision, but that's a topic for another time. So how do we do if we're trying to cluster on this very deliberately terrible data set? Well, I think it's worth noting that k-means did worse. I was actually very proud of this because the semi-definite results, they have their downsides here, which I'll get to in a second. But the algorithm did perform noticeably better than k-means, particularly when it did have the ground truth to compare to. So ground truth would obviously be the labeling of each digit according to where it belongs. And the correct number of clusters to look for in a set of digits, a randomly selected set of digits, would be 10. So when I ran these experiments, I did randomly select 50 to 60 of the handwritten digits, which did also mean that occasionally I would select a set that actually only contained samples of 9 digits. And I wanted to see how both of these algorithms would perform on that. And what you'll notice is that if you look again at the scales on the y-axis, because that's something I need to learn how to fix in Python, k-means actually gave us very poor results when you look at how it did compared to the actual labeling of the images. Semi-definite programming, we do still get this nice elbow shape. So this is the RAND score. Remember, higher is better for RAND. And if you were going off of k-means, first of all, k-means didn't do well at any point. And second, you might be inclined to believe that there are 15 digits in the human numerical system. Unfortunately, the results did not come through quite so cleanly when we took away the knowledge of the ground truth. Now, k-means still had a really hard time with this data set. But for semi-definite programming, you can see that that sharp elbow has been completely removed by how messy the data is. And to get a visualization of sort of what was coming out of this, I decided to try taking the clusters that the semi-definite programming would give me for k equals 10, averaging the images in each cluster and seeing what it spit out. And you can tell from this type of sample that what it really comes down to is it handled some digits better than others. 5s are pretty clean. 8s look pretty clean. 0, that's probably mostly 1s. That's 9s. No idea what that is. That's a collection of all the things that didn't nicely fit anywhere else, is what that is. But overall pretty decent. There was one weird quirk that I noticed during these experiments, though. So since I was selecting which digits I was going to be trying to cluster at random, unlike my nice data set earlier, you'd often get really skewed numbers of how many of each digit were in the set. So for example, these histograms are from a case where I had 11 6s in the data set that I sampled, and only 2 each of 8s and 9s. And when I looked at how many things iterated linear optimization put in each of its 10 clusters, what I noticed was that it would regularly bias towards a more evenly distributed histogram. Now, k-means did not have this problem. K-means wasn't doing so well at clustering, but it wasn't doing this smoothing of the distribution. And I do have a theory as to what might be causing this, and it really comes down to the geometry of the k-way elliptope. So just to throw out a couple of numbers on this, this would have been a case of n equals 60, k equals 10. And if you think about the number of sort of skewed partitions that you could get by trying to sort 60 elements into 10 groups, the number of drastically skewed partitions matching those conditions is going to be very much outnumbered by the more evenly distributed partitions. I don't have a good strictly quantitative representation of that yet, because I would need to sort of cleanly define what I mean by skewed versus even. But basically what I'm getting at is that the space of possible vertices has gotten so large at that point that it becomes difficult to find sort of the optimal one. Now, I believe this is also the same sort of problem that makes it so that when I choose a very high K value, that the algorithm is no longer able to drop back down to the true one. I've simply added too many vertices, too many fixed points. And so the algorithm will end up somewhere, but not necessarily always at the absolute ideal. Okay, so that's a lot. I do have a couple of future directions that I'm interested in pursuing based on all of this. Number one, between the two extremes of my carefully generated data and the incredibly messy handwritten digits, there should be some way to say, if the data is sufficiently nice and I give the algorithm the correct number of clusters to look for, then it will find the correct clusters. So that's something I'm going to be looking to prove. Initially, my conjecture is that the maximum distance between any 2 points in the same cluster needs to be smaller than the distance between any 2 points, or than the minimum distance between any 2 points in different clusters. But that might need to be revised to just find some bound, any bound. The next thing that I want to look at from both a combinatorial and geometric angle is this question of why the algorithm appears to be avoiding, or perhaps simply not reaching, the extreme skewed partitions, even when these are the ground truth. I suspect this is going to be related to the regions of attraction of the fixed points in the large elliptopes. And so I'm going to examine that geometrically, as well as trying to enumerate how many extreme versus normal partitions are available. And finally, this is not the only semi-definite programming-based method to be tested in recent years. And so one thing that I really want to do is directly compare this rounding step to the rounding step ideated in another recent paper. And that's something that I've been working on very recently. I was hoping to have results available for you all today on that, but it has hit a couple of programming snags, and I'll have to update you later. And that's all I've got. Any questions?
Let's first give Teresa a round of applause. And now, if there are any questions.
I have lots. But I guess the first question, actually, I want to kind of go way back to the geometry of the K-way elliptopes.
Absolutely.
So you start with an elliptope, and then you cut it with a bunch of hyperplanes.
Mm-hmm.
And so you actually said that you kind of had the polytopic part of the elliptope, and then you had kind of the original part on your boundary.
Yes.
As N and K grow, it feels like, are you only ever going to have one vertex that is still kind of puffy all the way around the vertex? And it feels like this becomes almost entirely polytopic as N and K grow.
Yeah, so that is what I thought initially. But the computational results don't appear to hold up to that.
Okay.
So the thing is, if it was a purely polytopic space, basically what happens is, So when semi-definite programming gets you to somewhere on this thing or in this thing,
Right.
it's not necessarily on the surface. How the algorithm typically works is the first step will put you on the outer surface of the elliptope, and then it'll start stepping towards somewhere.
Okay.
If we were in a polytopal region, what I would expect to see is that it would only take a single subsequent step to get to a vertex. I've run some, or I've done some theory work on how this algorithm behaves on polytopes, and it's a lot faster. It only takes, once you're on a affine space, it really only takes a single step, because determining the maximal dot product question, once you're on a polytopal space, that has to be one of the vertices of that thing. So that seems like it should be the end of it. But instead, when I run these experiments, what I'm seeing is like the number of steps that it takes to find a vertex is very unpredictable. And so what I kind of have to conclude there is that there's a lot more non-polytopal space out there than I'm giving it credit for.
Okay, that's interesting, because yeah, like you have, the polytopal approximation, the elliptope, where you just take the vertices and make it a polytope and say, yeah, it's not the same. I was just curious to see how different the results were on the truncated elliptope or the planed off elliptope, and it sounds like you've been playing around with that already. But
yeah, if I had to guess, I would say that the primary issue is that as you add dimensions and as you slice off spaces, you'll get those polytopal faces, and you'll get like the little facets that are nice and flat. But I think they're all going to be relatively close to each other compared to how close they are to this other thing.
okay.
I think that might be part of the problem. But again, this gets into the issue of we can really only draw the elliptope for the n=3 case. And so it's very difficult to get a handle on what it actually does at higher dimensions.
Right. Okay, I've got a couple more questions, and then I have to go because I'm stepping in for someone else's lecture, but I want to let other people ask questions. Okay, I don't see anyone jumping in. Second question, you were talking about how it seems to be bad at finding these partitions with like high variance in the parts or whatever that.
Yes.
Did you gave this original example where you had these nice Gaussian distributions around a circle. Did you run that experiment where different Gaussian, like how much variance are there in the number of points in these Gaussians? Like, do you have a version of this where there's only 3 in one group and 17 in the other?
Right. So that's not something that I ran initially. It's something that I'm definitely coming back to, having sort of made this realization that this seems to be something that it's doing. Because when I originally ran the tests, it was, coding convenient to just choose a number of points that I was going to select from each of my sort of sets.
Right.
But yes, one of the things that I'm going to do as part of my exploration of this behavior is going to be to go back and keep the nice structure, but now with a more randomized selection of how many points from each data set.
Okay, yeah, because I find that interesting to see how much of that was noise and how much of that was this observed phenomenon. My final question, I think I might have time for, is early on you brought up the issue of, depending on how you define successful clustering, like can you find stripy data sets, or are you just trying to kind of cover your data set in circles? So I don't quite catch. So how does your algorithm make that decision? Is that mostly encoded in how your starting point for your iteration?
It's, yeah, so it's an important thing to mention related to clustering problems. Because that's one of the biggest issues with like selecting a good algorithm when you go to cluster.
Yeah.
However, in this particular case, that depends more on how you set up the semi-definite programming problem and the distance metric. So it's a
Okay.
really important component of what's going on here. Like the reason I'm looking at a semi-definite algorithm is to allow for more of that flexibility. But the rounding step itself, the iterated linear optimization, is sort of more the focus of my research. And so I haven't really been messing with that too much.
Okay, but that is that distinction there is accounted for in the step of first getting onto the ellipto. It's
Yes.
okay. In the sure, and because I would be like, I see this and it's like, oh, this could be covered well by circles, but what happens when you just have like 10 stripes? And I'm like, oh, that's also interesting, but I understand that
Yes.
you can have 80 questions. You have to tackle them in order.
Yeah. If I wanted to run data that looked like that sort of stripy sort of setup, number one, it would be very useful to know ahead of time that it was doing that. But like supposing that I did know that in advance, probably what I would look into would be just sort of an initial coordinate change, some sort of scaling to bring them back into nicer groups so that I could use Euclidean distance again. But an
Okay.
alternative would be to look for a distance metric that more explicitly favors those stripes.
Sure. I guess my question is like, yeah, you can someone, you can come up with an algorithm, someone else can come up with an algorithm that may or may not be good at detecting stripes. But it sounds to me that, okay, I am trying to detect 12 stripes. There are only 8 stripes. The question is, does the iterated linear program go down from 12 stripes back down to 8 stripes? Which I don't, is the iterated linear programming I guess that's your dot product. You have to come up with the correct dot product for stripe detection.
Yeah, something like that.
Okay.
But yeah, so the big benefit to this that we're really sort of honed in on is the fact that it can explicitly identify that there should be fewer clusters than it's been told to look for.
Right.
And this is without any sort of machine learning. This is completely absent any artificial intelligence aspects. This is purely the math.
Yeah, no, it's very interesting. I have run out of time.
Sure.
I'll ask someone else to stop the recording.
I got it.
Thank you.
Yeah.
All
Other
right.
questions?
Are there some nice applications you have in mind? So
Yes, so actually this project was originally inspired by a collaboration with a faculty member in the School of Public Health who was concerned about sort of making sure that an algorithm like this would actually be applicable to public health data, which sometimes deals with numerical scales that are kind of weird, sort of compared to other forms of data. I mean, if you want to think about even something as simple as like various human medical data gathering things, you could talk about the concentration of different substances in the blood. You could talk about oxygenation level. You can talk about heart rate, and all of those are going to be working on very, very different numerical scales from one another. And so part of the inspiration was really making sure that there was something available that could work as sort of a catch-all, something that would really not have its results, something that could have its results influenced by those different scales, but not completely dominated by it, looking for that kind of middle ground. So that's one thing that we're looking at pretty strongly.
That's awesome. Thank you.
Mm-hmm.
All right, let's give Teresa one more round of applause. And I guess we can stop the recording.